large language models and fine tuning. So we are basically going to go through and just understand, what fine tuning and fine tuning actually means, and then perform that in a few different ways. There's quite a few different ways that you can modify a model, and we'll see a couple of those examples. And then the second part, we're going to look at using Retrieval Augmented Generation, RAG, for adapting sort of models to suit our data and our workflows. We've got 2 hours, I think, booked in. I think we'll get through it sort of faster than that. I'll aim for a break on the hour, so in about an hour from now, and then we'll probably just finish up in a few minutes after a short break. All right, so we'll talk also as we go about the hardware requirements and limitations. So if you're not familiar with sort of the concept of GPUs, TPUs, or CPUs, and why they sort of work better, or which ones work better for AI models. And we'll understand how to prepare our data for training, for tuning. And we'll be using, in particular, a tool called Keras. And we're going to be using a TPU backend. Hopefully, we'll see if that works. And then we'll also look at using a different library called transformers. And we'll understand what this parameter efficient fine tuning means with something called a low rank adaptation, or the LoRa method. And we'll see how good we can train some models, and then we'll compare it with RAG in the second part. All right, so we're all probably familiar with large language models at this point. They're these gigantuan beasts of things that try and understand the human experience, but under the hood, they're just a matrix of numbers that have been shown lots and lots of different data. So they've been shown mostly text-based data. We'll talk about text-based data in this context. They have other models have been shown sort of different images, and there's multimodal models, but we'll stick to text-based for today. And they sort of learned how sentences, how words, how language is structured. And based on the context you give them, the prompts that you provide, they can delve into their knowledge base, and they can try and connect with you and relate to the prompts that you're providing. It's going to try and predict, what the most likely prompt is, or most likely response is that you want back. And so that's a large language model. And now fine tuning allows us to take these massive models. So the proprietary ones, the ChatGPTs, the Geminis. We don't know how many parameters. We'll talk about this word. We don't know how many parameters they use, but it's probably in the order of like trillions of parameters, which basically means building those and executing those on your own hardware is very prohibitive, just due to you need massive amounts of usually GPU capability and RAM to both train them and then also execute them. But what you can do is take these powerful models and distill them down, or you can bolt on sort of extra bits of information that you want the model to know, and it's already got all its sort of knowledge and understanding of how things relate to each other, how context, how words string together, how code is formatted, and it takes that and then it adapts it to your data. So that's the benefit of finding, and then you can have quite targeted and sort of smaller models that you can put into your pipelines. Okay, and yeah, generally, so the way they work, they're basically doing lots and lots of matrix multiplications when you're performing sort of deep learning or any sort of AI, and that works really well on a GPU card or as opposed to a CPU. So CPUs, they're usually really fast. They can operate on like single threads. Maybe you've got multi-threads. Maybe you've got like 32 cores or something on a really big CPU, but it can still only solve sort of 32 equations simultaneously. But when you're doing deep learning, you're solving sort of thousands of simultaneous equations. And so that's where GPUs come in, because they have, they basically have thousands of cores that can solve these equations. And so it's a tensor processing unit that is kind of like a GPU, except it's been specifically designed for tensor calculus. It's a GPU that doesn't have the legacy of being a graphics processor. Instead, it's it's just made for tense processing. So they're quite efficient, and they are very good at doing lots of AI tasks. And so we'll hopefully use one in a second. So we'll talk about model architecture as we go. So the architecture is often, let me step back. So there's something called a framework and an architecture, I guess. So there's a few pieces that go into both using a large language model and creating a large language model and interacting with a large language model. So the architecture is often things like Gemma or GPT or Llama. These all have sort of they're all pre-trained models that have specific training architecture. So the architecture is kind of like the code and the rules that perform the pathway through the neural networks that take your tokens, the prompts that you put in, goes through the neural network, and it comes out the other side. So that's like the architecture of the model. But then often the model comes in two pieces, and we kind of obfuscate those pieces. The other thing is the weights of the model. And so when you have like an open weight model, you often have the so things like Gemma are open weights, and so we know we're provided what the trained model looks like, but we don't actually know the architecture, I don't think, with Gemma. But then other large language models, they provide the architecture as well, so you can see sort of what code was written to train those weights. Sometimes it can be reverse engineered pretty accurately as well. And now the framework, this is sort of the library and software libraries we use to interact with those models. So everyone who makes a large language model, they might just save it in a slightly different format. They might have, a 1,000 by 1,000 matrix. So if you go to read it with the one framework, it might not read in with the default values. You have to use something else. And so there's different frameworks that we have to use to interact with different models. And some models, usually you can load a model in and convert it to another framework. And yeah, we can talk about that more as we go. But the ones that sort of are very popular, so you may have heard of, are Keras, which we'll use today. Then Hugging Face Transformers is one, TensorFlow and PyTorch, and there's sort of a whole bunch of others as well. Okay, and so the rule of thumb is we have to use a framework that supports the model architecture that we want to work with, and sort of vice versa. And when we download our model for the first time, we'll get into that. Okay, so that's a 10,000 foot overview, but I like to get our hands dirty with all of these things. So we're going to start with a Google Colab notebook. So if you click that link in the notes. So if anyone is joining, I'm sort of just up to about there. So click that link and it should open up Google Colab. If you have a Google account and you're logged in, hopefully, you may have got what happens when I click it? It might, so it might give you this prompt. You can just click New Notebook and it'll open it up. That's sort of what we want there. A new notebook, and it should look something like this. I'm just going to zoom in a little bit so I can see. Okay, hopefully that's enough real estate. And at the moment, it's waiting for us to put some Python code in. So I'm hoping everyone has just some experience with Python here and the notebook concept. If you don't, just maybe ask questions in the chat or something, and we can sort of catch you up. But basically, what we're going to do is this is like a Python instance in the cloud. So Google Colab, it lets us run sort of Python code. I think you can run R and Julia as well. And it gives you a free virtual machine that will give you some resources when you connect to it. I haven't connected yet. There's a connect button there. But what I'm going to do is go up to runtime. I'm going to go change runtime type. And we can see here, I can pick a few options. So there I can go Python R Julia, stick with Python 3. And then it says hardware accelerator. So I'm just using the free Colab. And so it's got a couple grayed out. If you pay for Colab, you can sort of get more resources. And I'm going to pick a TPU over here. And the runtime version, I'll just stick to latest. But there are sort of previous versions which have kind of like older versions of Python and older versions of model frameworks and, and different packages. All right, I'll click save, and hopefully now I'm going to click connect. Hopefully that should work. It may not have resources, so sometimes you don't get resources available. I was lucky enough. I've been allocated a TPU. Fantastic. It says I've got about an hour and 50 minutes currently, so that sort of refreshes regularly, and it gives me specs about the machine as well. So I'm using this TPU. I think it's a V5 TPU, 47 gigs of RAM and 225 gigs of storage. Fantastic. And I'm going to now put our first bit of code in. So I'm going to basically follow this along, and hopefully, yeah, I've got it open in another window, so I'm not just I haven't just memorized or anything. But follow this along. Everything I type and write out will be here. If you get lost or I go too fast or something. Okay, so I'm going to just import a few packages to get us started. So I'm going to import something called OS, and I'm going to import something called pandas as PD. So I'm importing OS, which is like operating system functions that lets us do some simple file manipulations. I'm importing pandas, which will let us deal with some data that we're going to load in. And I'm also going to import Kaggle Hub, and I'll talk about that in a second. Kaggle Hub, all one word. And I'll start with that. I'm going to execute that. You can click play, or you can press Shift and Enter. It usually does the trick, and nothing happened, so that's usually a good sign. So I think I've imported things successfully. I've got a little green tick there. Okay, so the next command is going to be Kaggle hub.login with a parentheses, and then we're going to go visit Kaggle. So I'm going to run that, and this says, "Hello, welcome to Kaggle. Please post your API token." So let's go get an API token. Okay, and I'll talk about Kaggle. So Kaggle's a platform. It's usually for well, traditionally it started as like a data science or machine learning competition platform, and then it sort of expanded its use cases where not only can you go in these competitions to sort of optimize code and everything, but you can also host models on there, you can host data sets on there, and you can they have notebooks on Colab as well, so you can use Colab resources, notebooks on Kaggle as well, so you can use Kaggle resources. And so today we're just using Kaggle to download some data sets. And so we'll look at those data sets, but we need what's called an API token. So I've posted this in the chat, and it should hopefully take you to this page once you're logged in. So I'm logged in, and here is my API tokens. And this is basically like a password that we use to connect to Kaggle and authenticates us, and so we can download data pretty much. You can download it in other ways too, so you don't necessarily have to do it this way, but we'll do that today. So I'm going to click Generate New Token. I'll give it a name. Let's call it Fine Tune. These are very disposable, so never share this with anyone. So I'll delete this pretty soon. But basically, I'm going to copy that token, that API token at the top. I'm going to go back here and I'm going to paste it in and click Login. And it says I've set and validated. How'd everyone go? I think that's the most technical hurdle that we have to get over today. Fantastic. Love all the thumbs up. Okay, cool. So once you're logged in and we're authenticated, we can start downloading data. Okay, we're going to download 3 different data, I guess. We're going to download 2 models and 1 data set. And so, so we go to, the ones that I'm getting are, let me actually go to Kaggle, close that, home, and I'm going to search for Gemma 3. Great, so there's Gemma 3. There's ones from Google and there's ones from Keras. Oh, good stuff, Richard. Glad you figured that out. So we'll use this lightweight Gemma 3 model today. Now, you might have to click on consent. So I'll just post this in the chat. Yeah, there's probably, like, if you haven't been to this page ever, there's probably a button here that says, like, you have to agree to the license to use this model. So you can just click on that and then scroll down and click, I accept or something. Okay, and then here, this page basically describes how the model works, what it's used for. There's thousands of models hosted on Kaggle. And it says the context window, so how many tokens, how many words we can pass the model. So this is a 128K context window, which is quite large. You know, models used to have about 8,000, probably even less, context windows, and it's got multilingual support, and it describes, you know, how it works. So some of these are they're multimodal, so that you can put images as well as text, and they come in a bunch of different sizes. So this is the interesting part, and it also talks about the training data set, what it was trained on, and, you know, it did some pre-processing. There's some sort of like hard-coded things in there, and it says how it was trained. So lots of sort of interesting information about the model. And then it gives some benchmarks, like how it performs on these various benchmarks. So usually the higher the number, the better. And you often see new models come out and they sort of supersede previous ones. Okay, but if I keep scrolling down, there'll be, so down here at model variations. So I mentioned the frameworks. So these are all the different frameworks. So they're called model variations here. We're using Keras today, but if you were using PyTorch, you download the PyTorch variation, or Transformers, the Transformers variation, or any of these other ones. And so we're using Keras, so we have to then pick one of the variations, and there are, again, about a dozen or so options that we have, and it can be very, very confusing. Basically, the bigger the number, so the big number there is 27B, 27 billion, means you need a much larger GPU or TPU. As a rule of thumb, the VRAM, so the size of the GPU, the amount of RAM on the GPU, not like computer RAM, should be about the size of the number to fit on there. But that's a rule of thumb. And we are going to use a very small model today, just for demo purposes. We're going to use the 270M model, but in fact, I want the Instruct 270M model. So that one there. Super. And then you can download it. There's a bunch of different ways to download it. So you can use it via Kaggle Hub, which is what we're going to be doing. Kaggle CLI, curl. So you can curl basically means you can download it directly. You can also just download the model there as a zip file. But we're going to use that code there. So it looks something like that. So I'll go back to my notebook. I've just copied that, and I've got path equals Kaggle Hub model underscore download and Keras Gemma 3 underscore instruct 270M. I'll click go. Oh, okay. I don't have permission to access this. Okay, that's interesting. It's a problem there. So I've authenticated. Have I already downloaded this? I don't know if anyone else got that. If you haven't clicked the consent, you'll get that error, or if you haven't authenticated, you'll get that error. I'm just browsing I have noticed there's a little bit of a, I think it's a bug or something. If you've already downloaded it before, it will, it basically gives you that error. All right, it's, okay, why hasn't mine? Maybe I'll just log in again. I'll go back to my, oh yeah, other people have got the same issue. Let's try, how about, let's go the 270M one then. We can always just try a different model. Okay, I'll try the 270M model, see if that's any better. Nope, okay. All right, let's try, okay, if that works, fantastic, use that model. If not, we can even try the Gemma 4 model. Wonder why that wasn't working. So Gemma 4, it's a new model. The reason I'm not using this updated one is just because, oh, actually, no, I won't use Gemma 4 because it's going to be like a different framework and everything. So sorry, I'll go back. Let's go back to Gemma 3. Oh, Gemma 3. Yeah, that's quite odd. I have noticed that that particular model, for some reason, it sometimes doesn't download. Okay, let me get the 1B instruct. It might be a little bit. Let's see if that one works. Path. Come on, 1B. No, okay. Why aren't you working? Kaggle Hub model dub. Okay, that's okay. I can use one of the other methods. Let's see if this works. Let's download this curl Kaggle username. Will that work? Oh, that probably won't work. Expert API Kaggle CLI. Will that one work? I don't think that'll work actually. Follow the instruction to authenticate. Oh no, that's, oh yeah, okay. We can do this. I'll run through what I'm doing in a second. I'm just gonna get my token again. This is great. Things never work the way we want. Generate new token. Generate. Copy that one. Let me log in. Paste. Probably don't need to do that. Oops. Export. Okay, let's try this one. Oh no, it's not working. Okay. Oh, that's quite a bother. Okay. Let me try one more thing. I can do this. I can go to, let's go to Kaggle Gemma 3. So some people's work, that's good. Yeah, I got this error last week as well, but it worked for me later. Okay, so let me just download, okay, 270M instruct, download, and I'm just going to download the tar.gz. There we go. So that's about 400 megabytes. It's downloading. I'm going to upload it to here. And then it should work. Okay. So I've just downloaded the zip file. Okay, it's still downloading. And I'm literally just going to drag and drop it into my content folder. Okay, good. I think, is that finished? All right, then I'm going to, will this let me, I think I double clicked it. Oh wait, sorry, is that downloading or uploading? Thinking. Okay, and I'm going to go tar, I'm going to put this xzvf / content / Gemma super. All right, good. Let me refresh that. Okay, I think we're in business. So, oh wait, I'm still uploading. Sorry. Let me try again. Has it finished uploading it? Oh yeah, no, it's saying, okay, I'm going to put this in the chat. Once again, okay, so the workaround there, I've just clicked download the model as a tar.gz file from here. That downloads, it's functionally a zip file, just in a different format. You can then just drag it into your Colab. So you can drag it into this button over here, which is like the folders. Put it in the content folder, which is sort of your user space while you're connected to Colab. And then and then when it's finished uploading, you can execute this command and it will unzip it. And so I put that in the chat. Basically, that command it's actually a Linux command. So we're on a sort of Linux virtual machine here, and that says untar this file, so like unzip. And these flags just mean extract it, make it verbose. It's a zip file or a gzip file, as well as being compressed in a tar format. And I forget what the F means, but yeah, basically that will unzip it. All right, and then hopefully we'll be back on track once that's finished. So the next step will be to set up our TPU. So we're going to set up our TPU so it's sort of ready for our model calls, and we can do that sort of whilst it's uploading and downloading in the background. Okay. Yeah, I think there's actually a bug with this, because I've had this problem like a couple. It's been intermittent, so I haven't been able to tell when it occurs when I use this Kaggle Hub download for the Gemma 3 ones recently. But yeah, we'll figure it out. Okay, so we've got a TPU here, and we want to use it. So anytime you use a GPU or a TPU, it usually just requires a little bit more code than normal. So but thankfully it's pretty straightforward with Keras, and we're under the hood. We're going to use something called JAX as well. So a lot of things, moving parts, but I can unpack things as we go. So I'm going to run this command os environ and then Keras in all caps backend equals JAX. So Keras is basically a high level. It's a high level interface for interacting with AI models. And so it takes away a lot of the complexity in code. And I'm going to show an example with transformers, where we can see like we have like 1,000 options, which makes it very powerful, but it also makes it very confusing. So Keras just sort of makes things a little bit simpler for us. So I'm going to set that and say we want to use the backend JAX. And so there's different ways like that all we interact with the GPU connected to the model, connected to like our front end code. And so we're going to be using JAX in this case. Other options there would be PyTorch or TensorFlow, but we'll use JAX to sort of do the maths for us in the background. And I'm also going to set this one, os environ XLA underscore Python. You can copy and paste from the notes if you like. Client underscore mem fraction equals 1.0. So this just means we say we want to use all the memory on our TPU for us. So if you're on a shared machine or something, it would kind of like be like, it would check if other programs were running and wouldn't want to like make those crash or make your one crash. This one we just say, just give us all the memory. Okay, so we set those two things. And then when we import our libraries, we're going to go import JAX. And I'm also going to go jax.config.update, and then JAX underscore platform name. And I think JAX and Keras are pretty good in that I probably don't even need to do this. it could figure out if I had a TPU, a GPU, or a CPU, and would do it. But here I'm explicitly setting the TPU. Hopefully that worked. Good stuff. It didn't error. Okay, and then I'm going to import Keras, and I'm going to import Keras Hub. So that will be the, I think I've got Keras Hub. We might have to install that. Okay, so meanwhile, let me just check. I'll execute that again. Oh, no module name Keras Hub. Okay, I need to install one more thing. Sorry about that. Let's just go code. You also need to run this one. Pip install Keras. Oh, actually, I'll do, yeah, no, that'll be fine. Keras underscore Keras dash hub. So, okay. So pip or PyPy, that's the way we install additional Python packages. And these are all the packages we've installed imported so far: OS, Pandas, Kaggle Hub, JAX. They're already installed in Google Colab by default at some sort of version. But we also need this one, Keras Hub, which isn't there. And you can use this exclamation mark pip install Keras Hub to install that. And hopefully that should work okay. And then I'll try and run this again when that's finished. Okay, so we install that and we import it, and then we should be good to go. Oh, actually, sorry, I haven't downloaded the other two data sets as well. So we'll get there. Yeah, we'll do that one in a second. We'll do medcord. Okay, super. So let me check. Okay, cool. So it says successfully installed Keras Hub. Now, if I go back, I'm just going to run this cell again. So generally with the notebook, you run sort of from the top down. But if you can sort of jump back and forth, you just have to keep in mind, like we ran this installer after that, but then we went back and ran it again. So this now becomes sort of the one would run again. We don't have to run this again. Hopefully that makes sense. Okay, all we've done is sort of imported our packages, set up our environment, downloaded our data. Sorry, I'll run this zip again. Hopefully it works now. Working this time. Super duper. Okay, that looks like it works. Fantastic. So we have a large language model there. There's nothing like mysterious about these models. They're literally just, you know, files. One is the weights file. So that's the big one that it's in this HDF5 format. And it's a way to store like the big tensor matrix. And the other ones are like the metadata ones that describe the architecture. And we'll point to this in a second and use it. Okay, so now we also need to download this medcord data set. It's a question and answer data set from about medical data. So I'm just going to I'll just type it out. Path data equals Kaggle hub dot data set download. That was g threader slash medcord. Okay, let me run that. Super. I'll just write path data so I can see it. Yep. Okay, cool. So that now exists in that directory. I can browse to it. Where is it? Root cache Kaggle hub. It's thinking. There we go. Kaggle hub datasets gpreda medcord version 1, and it's just a CSV file. So I can actually just open it up if you want. I think it might be pretty big actually. But yeah, it's a CSV file. So again, nothing too mysterious or anything about that. 16,000 entries. Has questions like, what is our glaucoma? and then it's got an answer, and then it has some other metadata, the source, the focus area, and so on. And so there's lots of these question and answer sets. And we're going to use that training set to fine tune our current general Gemma 3 model. Okay, super. So we can read that in. So df equals pd.read CSV, and we saved it as this path data, but we also want to just append the CSV name, which is medcord.csv. Okay, and again, you can have a look at the data frame if you like. So that's what we're seeing there. I'll just delete that so people can see that line of code. Okay, and what we're going to do, just for training purposes, you know, we're going to look at this thing called pernicious anemia. So it's like a real technical specific thing that appears in the MedQuad data set a few times. So I'm just going to extract sort of all the bits of information that we want from that data set, from the 16,000 rows. So this is just sort of pandas magic, let's call it. If you're familiar with pandas, we're basically taking a, we're going to take a subset of the data of the question column for any strings that contains the words pernicious anemia, and I'll say case, so that means uppercase, lowercase is false. And if there's any nans, so if there's any like weird files or anything, don't load them in. All right, cool. And I also, I'm going to subset this again. So I'm, what have I got? Oh yeah, so let me just think. Maybe I'll just copy and paste that in. So df questions subset mask equals that. And then I'm going to say or else if it's df answer dot string dot contains. You can just copy this from the notes. Pernicious anemia. Again, I want case equals false and na equals false. Or I want to, if the df focus area, so if any of these columns have the words basically pernicious anemia in them, we are going to keep it, and if it doesn't, pernicious anemia. Right, case equals false, na equals false, close bracket. Okay, I've definitely made a typo there. Let me just run it. Oh, cool, that worked. So, and then we'll make the subset of the data. So I just made a mask that sets up like all these true and falses in the that data frame that we saw. So in the CSV, which will say, you know, which lines have pernicious anemia on it. That's what that's doing. And then the subset is the data frame where df subset mask equals true. And we can have a look at that as well when it's printed out. Awesome. So now we have, there's only a handful there. There's about, they all appear on the screen. This is about 20 or so question answers where this this term pernicious anemia appears somewhere in the question, answer, or focus area column. So we now have a data set, and the reason sort of like it's important to understand building data sets for fine tuning is I think, you know, difficult. So getting it into the right format and everything is important. And in this case, we're building this subset of questions and answers. Maybe you just have like a big long documentation or something, or you've got a whole bunch of like journals or code or something, and you just want to teach it that, then it would be different. It wouldn't just be question answer. It might just be a big long string. So there's different ways that you have to sort of approach this. Okay, so now the next part. This is where we get into sort of back to the idea of frameworks, and the framework that we're using is Keras, and we're using the Gemma model. So we have to refactor our data frame, which is currently just a generic CSV file, into the format that Gemma expects. So if it's not Gemma, it would be in a different format. So every single model has like a slightly different way that it expects the data to be passed to it, and so what it's going to look like. Maybe I'll just copy this. So I'll just copy that. I think that'll work, and paste it in here. And I'm going to run it, and it's built this thing called formatted data. And have a look at it. It's taken that data frame and it's put it in the format that Gemma expects, which is basically you have to give it a prompt. So you have to give it a question, a list of questions in a dictionary. So that's very specific, a list of questions in a dictionary. And there's all the questions. And then the next key value in the dictionary is the responses. So there's all the answers to those questions. And so that's the format that Gemma expects. So you basically have to know that, go and read that model card and understand and know that that's what it expects in order to do the training. Otherwise, you get an error saying like, oh, it's not in the right format or something. Okay. Oh yeah. So yeah, Simon, back on the model card, which is back over here, somewhere buried in this, it will explain what it expects. Oh, here we go, features, prompts and responses. So it is there, not buried too far. But yeah, on the model card, that's where these things are written down. Usually, hopefully. Okay, then, okay, so we're basically, we're almost ready to go. We still need to load in that, this model. Let's hope it works. So if you, we have to load in the Gemma model that is not fine-tuned yet. So we're going to use Keras Hub. So I'm going to call this just causal LM. So it's a language model. You can call that whatever you like though. Keras _hub .models.gemma 3 causal LM. So this is why Keras is cool, because it has basically like a method or a function specifically for the Gemma 3 model set, a model series. So it knows sort of what data that they're in, what format they're in, what options are available. And again, if we go and look at this in the Keras documentation, you can read about it and see what options are available in this Gemma 3 causal LM class. And these are all the models that work with it. There's quite a few. But yeah, if you wanted to go and look at all the model architectures, like these are all the ones that are supported by Gemma. So you can see like there's all these, there's a whole bunch, some you might be familiar with. So Gemma 4 has its own one, GPT has its own one, Llama has its own one. And usually they're fairly similar, but they might just need a few extra bits and pieces. And so that's why Keras is good. Okay, so we're loading this in. That's all I'm doing. So I use from _preset. Now, if your download worked before, basically you can put the path where it downloaded to. If it didn't, you can find it on the disk. So mine is in content. I think mine's right there actually. So hopefully this works. Yeah, it's just in the, let me copy that path. I think it's just in /content. Oh, with quotations. It's going to work. So hopefully should find the JSON file in there and load it in. I think it's working, which is good. So it should basically, you point it to the folder that you've downloaded to. Okay, cool. So my model is ready to go. And if I do this, causal lm.summary with parentheses, this tells me all about this model. So, or it tells me a little bit about this model. So it's tells me how the tokens, so how the how the words it's been trained on, I guess, have been split up into specific chunks. And so that's the tokenizer. So there's lots of different ways you can do that. You know, you can do it one word at a time. You can do 2 words at a time. You can do half words at a time. So there's a specific, you know, Gemma 3 way that we tokenize words. So anytime you pass it a new prompt, it first runs through this tokenizer before it gets passed to the LLM. And so, and then it also explains whether it's got padding on it. So sometimes models need, you know, they have to all be the same number of characters. So it will just pad it with zeros if it needs to be the same size, or if it might pad it with something else. And then it's got the backbone here and the embedding model as well. And the interesting thing here is it has the total number of parameters. And so the parameters are basically like the number of like neural network connections, or the number of weights in the entire model. And that's that number, 270M. So it's approximately 270 million, which is really small for a large language model these days. But I'm using this one for demo purposes, so it's good. So if we downloaded the 1B model or the 2B, that's 1 billion and 2 billion, would see total parameters 1 billion, 2 billion, 27 billion, and so on. And yeah, so there's a bit of information about the model. And now let's set ourselves up for a baseline. What time is it? 2:50, cool. So let's set a prompt equals, what is pernicious anemia? And we can just set that as a prompt. So that's just the text string, and we'll use that as sort of our reference question. And if I go response raw, so this is the raw response before we've done any fine tuning. Causal LM dot generate, and then pass it the prompt. So pass it that text string, and I'll just print it out at the bottom when it finishes. This, hopefully, we're running on the TPU. It should be pretty quick. Usually the first time it takes a little bit of time, but then when you run it again, it's normally pretty quick to spit it back out. So if you're on the CPU, it would take longer. It might take about a minute or so, I think. Okay, but that should hopefully, yeah, give us the answer for the we haven't tuned our model yet. We've got our raw weights, and we're going to ask it a question, and then it will, based on this prompt, it will respond the best way the model can. So depending on the model you use and everything, it will give a better or worse answer. Now, if you put this into one of the Geminis or ChatGPTs, it would probably give a very well-reasoned and thought-out model. We're using a very small model, so they're a bit unwieldy. Sometimes they don't behave the way you expect, I guess, and they need a bit more caressing. Cool. Okay, so actually, yeah, it gave a reasonable answer. The answer is that is a condition where the body's ability to produce enough red blood cells is impaired. This can lead to a variety of symptoms, including fatigue, weakness, shortness of breath, etc., etc. Oh, and then it starts repeating itself. Okay, so yeah, that's where it goes a bit crazy, where it just kind of repeats itself again and again, which can happen with these small models because they're not that well. Yeah, they're a little bit harder to control. Okay, so next we are going to now fine tune. So this should not take too long. It's basically a couple lines of code. There's lots I can talk about though, but we want to we'll do the short training. So we're going to use LoRa. So I'm going to say causal LM. That's the name of our model that we've loaded in. Backbone, enable LoRa, and rank equals 16. So this basically says how many parameters should we free up to train, and usually multiples of like 2, 4, 6, 8, 16, and so on. And you often get like better performance when you don't retrain the whole model, because there's things like, you know, about dogs and cheese and whatever that have nothing to do with pernicious anemia that we would otherwise be updating. But we don't need to touch those things that have nothing to do with this. So we use this this concept of a low rank adaptation matrix, where we create sort of a new matrix that multiplies the existing weights just by the relevant nodes, basically. And that way it's much more efficient. Okay, so I enable that on there, and that should just go. And then we'll pass it some options as well. So there's a bunch of different options. Don't ask me too many details about which ones to use and everything. I think there's an artwork here. The optimizer, this is every time we show it new data, we basically need a way to say, like, are you doing better or are you doing worse? So we use kind of two key things, the optimizer and the loss function. And there's different ways to measure, you know, how well you're doing when you're, you know, dealing with text. Is it so we'll give it an answer that we know the answer to, and we'll give it a question and answer, and we'll say, here's what it looks like, show me your response, and then we'll test how well it did. And we can say, you know, how many words it got right in that set of words from the known answer, or maybe like maybe the start is more important than the end, maybe the middle is more important. So there's lots of different ways that you can measure that that overlap of accuracy. And yeah, so there's different optimizers. And the optimizer also lets us search through this the model space. It kind of jumps from randomization to randomization, looking for the right parameters to use, and the optimizer lets us do that. So lots of different options. Start with the defaults, I think, as a rule of thumb. Optimizers dot Adam. So we're using one called Adam with a learning rate of 0.001. Okay. We will also use, oops, in the wrong bracket. Oh, I need a comma there. And we're going to use the loss function. We'll use keras.losses.sparse categorical cross entropy, and from logits equals true. And the weighted metrics, to make sure, weighted metrics equals keras. Oh, that should be in a bracket. You can just copy and paste metrics dot sparse categorical accuracy. All right. I think surely I made a mistake there, but I'll run it. Okay, so I've module keras says no optimizers, just a typo. Let's try again. All right, excellent. So that worked. So I've compiled. I've now told the large language model to use LoRa. I've compiled the model with all these options, and now all I have to do is call this fit function dot fit and pass it the data that we formatted. Formatted data epochs equals 10 is a good number, and the batch size we can start with 1. Maybe I'll go 2. We'll see how that goes. Okay, So the epochs is the amount of times it goes through the data, and the batch size is how many questions and answers it passes to it each iteration, I guess. And so it'll take a little bit. Usually it's, again, usually the first one's a little slow, but then once it's going, especially on the TPU, it should be pretty quick. In real training, you'd probably use like maybe 100 epochs, and the biggest batch size, or usually the bigger the batch size, it can be better. You run into overfitting. You can over tune your model, and then it will only ever answer what it's been trained on, what it's been fine-tuned on. And so if you have smaller batch size, I think you can run into that. You can run into that problem. But then also, yeah. So there's trade-offs with sort of everything. You can set like early stopping, so it'll run through the epochs. It'll keep training and training as it's getting better. But then if it gets worse, it'll go back, and then it'll sort of finish and say, oh yeah, it's good enough. Okay, cool. So that's finished. There's only 11 data sets, so not very sort of 11 sets of the data. So it's not very big. These things are usually trained on thousands for fine tuning, maybe millions for the initial training. And while it's training, it shouldn't be too much longer. I can go causal LM dot make that same generate prompt. We'll have a break in a minute once it's finished. So I'm going to pass that same prompt again that we set up here. What is pernicious anemia? And hopefully that will give us a different response. I think in the notes there, I specifically say we hope the answer is better or more accurate, but really it's you got to have to think about it. It's it should be closer to what we've trained the model to do. So it's really important that whatever you're teaching the model, that's what you're doing. It's not better or worse. They're tricky words. All right, mine's taking a while. Let me know if people have. Oh, right. Okay. Sorry. The path. So the question of the path. If you downloaded your model successfully with the, let me go to the notes. If you downloaded your model successfully with, where is it? This command. Sorry, up here. With this command, then you can use path Gemma should be automatically set to wherever the model downloaded it. Because I had to download it and then manually uploaded it, I uploaded mine to my content folder. So then you can set path Gemma equals content, and then when you actually when you load the model in, so that's just pointing to a file in your computer. When you load the model in, which is back here, where is it? Here, that's where you can set that path Gemma to be wherever it is that JSON file exists in here. So wherever your JSON file or all the weights data exists. Hopefully that's clear. Okay, cool. So yeah, the other ones were much quicker. The first one took 161 seconds, but then it went really fast. And I'll run this prompt. Let's get a different response. And then we'll have a 5-minute break and stand up, stretch your legs, and then we'll come back and we'll attack the other topics. I just want to say this before I break. We can track the RAM. So my RAM spiked quite a lot during training. Yeah, if you're not on a TPU, this would, if you're on a CPU, this would take probably like maybe like maybe an hour, much longer. And you also might run out of RAM. So you reduce the batch size. Is probably the easiest thing if your RAM is ever crashing. And it depends on the size of the model and everything as well. Cool. So, oh, cool. It specifically mentioned vitamin B12 this time. So in our first one, it didn't do that. So I think that's actually, the pernicious anemia. It's a lack of vitamin B12. So we've definitely changed our model. We can even see the summary of it. We'll see these numbers have changed. So it's now 271 million instead of 268 or whatever it was before. And then if you want to save your model, you can do that and save it to disk, and it will again, it'll just be a file. You can go and where is it? There we go. There's my model. So there's a new model in there with JSON files and HDF files. Cool. Yeah, Mohammed asked a good question in there about these models are large language models. They're text-based models, but is there a way to fine-tune an LLM for numerical data? I guess I guess a large language model that's been trained on text, it knows what text is. It might know what some numbers are. If you then provided a bunch of numbers, I don't know how it would behave. You could give it a go, experiment with that. But probably what you want to do is start with a model that that's already been trained on numerical data. So there's things like AlphaFold has been trained on like protein sequence data. So it doesn't know what cats and dogs are, but it knows what GATCCA, like it knows what new DNA sequences are. And so there's other models like that. What's the one? There's I can't remember the name of it, but there's a model that's like just been trained on like CSV data, and there's models that have just been trained on time series. So they know everything about like time series. If you give it a new time series, it will be like, oh yeah, I've seen all these different types of time series. I've seen every type of like response in a time series and every feature. I've seen waves and oscillations and trend lines and everything. So I know what all those things are. So now if you give me your time series, I can probably make better predictions on that than just a generic one. So yeah, you probably want to start with one of those models. Okay, and yeah, thanks Richard for those details. That's good to know. So yeah, that's interesting. Yeah, I swear this code was working for me when I was testing it. So okay, now we have saved our model to disk. You can do whatever you like with that. You can download it or anything. I'm going to go through just one more example of doing the training again, just using a different a different model this time. So instead of using Gemma, we're going to use GPT-2. So that was sort of like a predecessor to GPT-3, which sort of was the one, 3.5, I think, was the chat GPT that sort of revolutionized or brought large language models to the masses. And so GPT-2 was it was a very lightweight model beforehand, and it's a good one to demo. And so the thing that is different here is that from Keras, we will use a different function or different class here called causal LM instead of causal Gemma 3 LM. So it just has slightly different options and functions within that. So to interact with it, and we'll also, this is the important thing that I really want to stress, is we have to set up like a different, we have to take that same data set, the same medquad data set, and this this function that we use to transform our data into the format that Gemma expects, it's a slightly different, but very, very important that it's different for GPT-2. So instead of having, I think we had a list of the questions and then a second list of the responses. This one, I believe, just has the questions and responses sort of tacked one after the other. So we can see that in a second. Okay, I didn't download this one earlier, so I'm just going to run that download line again. So hopefully this will be fairly snappy. We'll type it in. Let's see. So I'm just going to say path underscore GPT-2, just to prove that, you know, this does usually work. The Kaggle Hub model underscore download keras / GPT-2 / keras / GPT-2 underscore base underscore en, and I'll just print out the path GPT once it downloads. Cool. Okay, that downloaded far too quickly. Hopefully that wasn't a mistake. You can also check that out on GPT-2. There, dash GPT-2 models. There we go. GPT-2. You can read the model card. Similar to, I guess, Gemma has different informations about it. This one's even smaller. So models used to be smaller, I guess. Like a large, extra large model used to be 1.5B, and that's incredibly small by modern standards. And GPT-2 is more designed as a like next token predictor. This is how large language models started. Instead of being a sort of inferring questions and answers in context, it just predicted the next word in a sequence of words. But it has model variations as well that you can download. Okay, so once you've downloaded it, we then load it in just like before, but this time you can call it whatever you like. Maybe, yeah, I'll call it GPT-2. Why not? Actually, that might, no. I will call it causal. I'll call it exactly the same thing for one particular reason, in that I don't want to run out of memory. So by reloading in a model, it sort of clobbers the old one, and I won't run out of memory. So let's do that. Causal LLM keras underscore hub dot models. You could also just restart your notebook. Causal LM dot from preset. So this is how we loaded in Gemma before, pretty similar. And then the path GPT. Okay. And once that's loaded, I'm going to go causal LM dot generate, and then that prompt should be the same as it was previously, which was, yeah, what is pernicious anemia. Okay, you can look at the summary. You can look at the model details as well once that goes. Yeah, so this one's only 124 million, so it's relatively small. Okay, so this one, what is pernicious anemia? Pernicious anemia is a condition where your immune system is damaged by something. It can be caused by anemia. Anemia is caused by anemia. Anemia is deflation caused by anemia. So yeah, like that's pretty wild, but that's okay. Okay, so again, the important thing, yeah, writing this function correctly is probably the most important thing. I'll run that. So this took in our DF subset that we created before, and now it looks like this: formatted data GPT-2. Oh, sorry. Did I do that right? Oh, okay. So yeah, before we had, remember we had questions and answers, but this time we just had this sort of this big long string of lists. And it's very, like, it's similar, but it's not the same. So that's the important takeaway, is that it's similar but not the same. Okay, but now we have our data ready to go for training. Now we don't actually need to do LoRa. We don't need to do any PEFT, the performance efficient fine tuning. We can just fine tune the whole thing because we have a TPU and it's not that big. So we can just compile it. And this way I'm just using like all the default parameters. So I'm just showing you sort of like how simple it is out of the box. So we load in the model, we use this method called compile, and that gets the model ready for training. And then we call the fit, causal lm.fit. We pass it that formatted data in the GP2 format. Again, set the epochs equals 10 and batch size. Maybe 2 is not a good size because it's there's 11 there's 11 items in there. Maybe I'll set it to 1, might be faster. Okay, so yeah, it's literally like 4 lines of code. We load it in, and well, there's the function to get the data in the right format. We compile it and we fit it. That's it. So all you really need, and then hopefully that should do what we want again, and we can set up our prompt when it finishes. Dot generate dot prompt. Oops, generate prompt. Okay, and I'll execute that. So while we're waiting, feel free to ask any questions. Yeah, Akmal, it's based on your problem type. So yeah, guidelines for choosing the model architecture and framework. I think at the very end of this I have understand your task, pick your model, pick a framework, and build your pipeline. And so yeah, the answer's not always clear. Like the Gem, I think the Gem models genuinely are really like great models as a foundational set of models. So they're a great starting point. And then because they come in all different sizes, it's good. You're usually good to go. Framework, use Keras if you don't want to deal with too much. Otherwise, you know, if you want more options, you can use something else. And then yeah, understanding like your data and getting it in the right format. And so we spoke about that. How if you have numerical data, yeah, maybe don't use a large language model. Use a numerical model. Think about what you need to do. Okay, so I won't demo this one, but the transformers example here, it is basically the so it uses a different framework. It uses the Hugging Face transformers. So that's probably I would say this is like the industry standard method for fine tuning and for dealing with large language models. And as you can see, like the code is much more complex. Like you have to load in a lot more libraries. We have to we set we download a model, so that's Gemma 3 again. Download a data set. You have to set up the tokenizer as well. So before, we didn't have to do that. Keras took care of the tokenizer for us. That converts like our text, our training data into the tokens that that our model expects. Then we have to map it to the GPU in this case, I think, where I've got CUDA. I don't think I could get the TPU working immediately. Like it needed a lot more options with using transformers instead of Keras. So I used the GPU instead. And then, yeah, and you need to add like sort of all these other options before you finally get that's our LoRa configuration. We need to add all these target modules, which layers of the model you would tap to. Got to set these other parameters and training arguments, and set up this trainer, and then finally you run the training down there. So it just requires a little bit more, but if you need that sort of extra flexibility, like that's the way to go. Okay. All right, so let me check on this. How'd we go? Oh, it's still going. Oh, my session crashed. How about that? So I must have run out of RAM or something. That's okay. So I can quickly run it again just to show how few lines of code can do it. I'll log into Kaggle Hub. Where's I need a token. I keep forgetting my tokens. I just create them again. Make sure, especially, I know someone shared a token in the chat. Just make sure you click on expire token. and so it doesn't get used. So I'll log in. I'll set up Jax. We've got Jax, Harris Hub, and then we go down. Where's my okay? Download that and load it in. Well, I need the data as well. The data should be there. So, I need my data frame. Okay. Sorry. We're basically finished. I need that will crash. Okay. We'll see if that works. Anyway, we're basically finished with the fine tuning. Are there any questions? Oh yeah, Andrew. So your baseline. Actually, yeah, that is interesting. That if we ask the same. Yeah, that maybe there's a default sort of temperature which adjusts the what comes out of the weights, but we should have exactly the same weights, and we pass it the same prompt. Maybe there's some the default parameters allow like some randomness. I expect you could probably set that somewhere in one of the options to say like, don't just set the randomness to 0 or something, and then we'd all get the same response. So that is interesting that you did get something different. Has anything broken? I got Medquad. Download Medquad. Good. Medquad. Good. Path GPT. That's done. Okay, let's get that in that format. Good. Okay, compile. Batch size 1. I'll see. Hopefully it doesn't crash this time. Okay. Now, the next part. So while that's thinking, we can look at the second part of this session, which is the Retrieval Augmented Generation. So RAG, as it's known. And so as you can see, with fine tuning, it takes time. It takes have to do all this data processing, I guess. And usually you need a GPU or a TPU. RAG is much more lighter weight, and especially now that models have really big context windows, RAG can be quite powerful as a way to build up an entire knowledge base, and the large language model can just kind of pull in the relevant information from that knowledge base and inject the relevant bits into the prompt, and then ask the questions of your data. So it's kind of like the difference. And that way, if you get new data, you can just keep adding it to your knowledge base. Whereas if you fine tune your model, you'd have to refine tune it with all the data set for it to kind of be accurate. Otherwise, it might focus in too much on the new data. So yeah, fine tuning is generally much heavier, but you can distill your models down to really purposeful models that have specific intents, versus RAG, which is far more flexible, and you can almost update it live. So again, we are going to use Colab. I'll start a new one. Oh, it crashed again. Not sure why it's crashing, but that's okay. Because I'll start a new notebook. I'm going to kill this runtime. I'm going to disconnect and delete runtime. I'm going to start a new notebook, and hopefully, I'm going to try and get a GPU. Hopefully, it'll work. Okay, that one's dead. I'll try and get a GPU. We don't need a GPU, but it just it does go a lot quicker. So I'll pick a T4 GPU, and I'll click connect. If that works, we're happy. We've got to install Keras Hub, and we have to install sentence TF Keras and sentence transformer. So there's a couple of packages we have to install there. So I'll just, oh, cool, that worked. I got a GPU pip install. Oh, sorry, what do I need? I need, oh, where am I? Remove this. So I need Keras Hub, good. I need TF Keras and sentence transformers. Let's get those three things. So that's the first line of code. Let me zoom out a little bit. Put that in the chat. Where can you find the proper format for the model developing codes? I mentioned earlier, basically the model cards is probably the place to go. So here it will have instructions as long as it's been documented well. It should be, they might have examples of, yeah, compiling the model. Does it have a fit? Yeah, it's got a fit here. So there's a fit command there. So it shows you two features. We had 11 or so features. Yeah, the documentation, that's where you want to go, the model cards. Okay, cool. So I've just installed that. Very good. Oh, it's already satisfied. Super. Is it finished? It's finished. Okay, great. I'm just going to hide it by commenting it out so I get some screen real estate. Okay, once you've got that installed, the next step is to import all these packages like we did previously. So we're going to import OS, pandas, NumPy, Keras Hub again, Kaggle Hub. The new ones for us is this package called Sentence Transformers, and also a package from scikit-learn called, or we just want one function there called cosine similarity. So the sentence transformer, that is going to be used to build our RAG entity, and cosine similarity, that's going to be used for a way to rank how similar something is in vector space, how similar the word dog is to cat, how similar the word dog is to ball or to something. Okay. All right. So I'm just going to copy this in the interest of time, paste it in. Hopefully that all works. And then we'll have to log into Kaggle Hub again and go from there. So let's go Kaggle Hub.login. Should leave my token. I have to keep generating, because you only get to see these tokens once. So if you don't write it down, then you have to create a new one. But anyway, it's good practice to expire old tokens and secure. So I'll expire that one when I finished. All right, and we'll be good at it by then. Okay, so Kaggle login, very, very good. Again, that is just letting me download these models from Kaggle Hub, but as we saw, we can also just log into Kaggle and download them manually. So I'm going to download I'm asking to download this one again, so that now we know the way to do that. And we're also downloading this paraphrase mini LM model. That is our embedding model. So the embedding model is basically a way to project every single word, every token. It has mapped all these tokens and their similarities in some space. So yeah, like I said, it has put the word dog and possibly cat like close to each other. The word ball, that might be close to dog, but it might not be close to cat. The kennel might be close to dog. Then you might have wolf. Then you might have car or something, which is really far away from all of those. And it's not just in 2 dimensions or 3 dimensions, it's in some multi-dimensional space where all these embeddings can exist and these similarities between words. And so that's what this model does. There's a bunch of different models. Again, I've got a couple of examples written there, the embedding Gemma model, this all mini LM model. I think there's embedding Gemma 2 now as well. But we just need a really lightweight one for this example. So that's this paraphrase mini one, which is super lightweight. Okay, so I'm going to copy those 2 lines and I'll use that fix. So I had to do /1. That works. Good stuff. Oh, love it. Thank you. Put those in the chat. Okay. Oh, and I need that medquad data set again. Okay, so we're getting the same medquad data set that we had before. Good stuff. So we've got our path to our model, a path to embedding model, and our path to our data set. And yeah, they are just literally paths on the computer. So that was just a tricky way to download it and set that file path. So that's the path, path, and data is there, and path embedding model is there. Your locations may vary. You can set Kaggle Hub to download it to a specific place as well, but it's just put to a default place for now. Okay, and as before, we have we're actually this time I'm just going to load in the entire data set. So let me just paste that in, but I'll delete a bunch of it. So I'm downloading the entire, importing the entire medquad CSV file like we did before. I'm making this new sort of thing called combined text, and I'm creating this this object called documents. And you can imagine this is a set of documents. I think it's basically a list. So it's very big because it's the entire medquad data set. We're not, like before, we just pulled out the ones that had precocious anemia in. This time we're using everything because we can. And what the RAG will do, we'll just pull out the interesting parts to it later as we go. So it's got every single one. Oh yeah, so it's one big list. So it's a list with all that information, and then there's the next item in the list. So these could be, yeah, you can think of these as individual documents that may be chunked in different ways. So you've got, you know, they could be entire files. Maybe you'd pass paragraphs at a time. You can do it in sort of different, you can chunk it up in different ways. And we can talk about that as we go. Okay, now we do the embedding model. So let me just hide this. So again, screen real estate back. Okay, now we need the yeah, embedding model, which looks like, where am I? Embedding model equals sentence transformer, and then we pass it the path to the embedding model, which was just a path on my computer. So it's just like a where the weights in JSON file are located. And very good. It's loaded the weights for that model. And I'm also just going to go embedding model dot to. I'm going to pass it to the GPU. So it's very fast. Okay. So that's just a little command that'll speed things up a lot. Okay, so we've loaded in the model. We've got our data. They're in two places. Now we need to use our embedding model to take all of that data, all those documents, and put them into our vector space. So we need to, every single word in that vector, we want to pass our model over, and it's going to put it into the vector space that it's familiar with. So we'll pass the embedding model over the top of it and create what's called a vector store. So embedding underscore model dot encode documents. So this is the part that takes a long time. And when I say long time, show progress bar equals true, should only take yeah, a few seconds. This is to do every single thing in that medquad data set. This is on the GPU. On the CPU, it takes like several minutes, I guess, but it's still much faster than the GPU. You can do it on CPU, and you only have to do this once. So yeah, it's pretty performant. It's pretty good. And once you do it once, you've got your vector store and you're ready to go. Now, if we were to ask a similar question, so our question might be, what is anemia? Anemia. Okay, and then we go query embedding equals embedding model dot encode, and we encode our question, our example question. called it example question in the notes. And I'll just print it out so you can see what that looks like. So we've got our vector store that has all our documents embedded in vector space in some way as per the model. We then do the same thing with just our little question. So our little question, we encode that as well. We put that into vector space. And that's sort of what it looks like. It's represented by this huge matrix of numbers. And so every single token looks something like that. And we want to find where this is similar to all the other items and pieces inside our vector store. So we have this query, and we're going to compare it with our entire vector store. So let's see that. And there's a few different ways that, again, how you match these things up. We're just doing something very similar called simple called cosine similarity. Similarities equals cosine similarity. And we call that query embedding vector store. So we're literally, comparing our query embedding with the vector store, and we're finding the similarities between those. I can run that, and I think similarities, this will, that's basically a huge array, giving it a score between every single item in our vector store and the query embedding. So numbers that have the words anemia, in the vector store, things that have anemia in it, they'll get a higher score. Things that don't have any of those question sort of shape in there will get a very low score. Okay, and we can pull out these top, let's say top n. Let's get 3 top indices. So I'm just going to pull out the similarities. I'm going to pull out basically the top performing numbers here. So I'm going to search through that entire array. I think there's sort of hundreds of items in there. And so this is just some tricky Python to pull out the top 3 and print them to the screen to get, I'm going to get a couple numbers out, indices. So at array number 1,245, 8,180, and 8,178, there are 3 items that best match this question. What is anemia? Somewhere in that big document store. Okay, good stuff. And now we can actually get those documents. Retrieved docs equals documents I for I in top indices. And I'm going to go rag context equals, I'm just going to write some strings here. You'll see. So I'm just saying print some text. Because this is a text model, I have to basically, again, transform everything into text, some sort of way that the model will retrieved docs. Okay, surely I've made a mistake there. And I'll just print out that rag context as well. Cool, I didn't make any mistakes. So what it's done, it's pulled out the things from the vector store, and it's turned those indices back into text just so humans can read what it actually is. And there's the first one. I put these /n's. These means new line, so the model will see that and be like, oh yeah, start a new line, a couple new lines there to differentiate them. I think if I print it, it will actually obey the, oh yeah, it formats a bit nicer if I print it. So these are the chunks that it's pulled out. Okay, good. Let me hide that. And now we can, again, do exactly sort of what we did before. We establish a baseline. So back over here, we can establish a baseline with our model. So I'll load in this model, Gemma causal LM. Hopefully that Oh, it's downloading it. Whoops, I forgot to point to it. That's okay. And so this one, I've made the prompt a little bit more verbose. So I've said, instead of just saying, you know, what is anemia or something, I said, I gave it like an instruction and said, answer the following question, and then the question, and then it gives me this question that I put in there. Sorry, I've called that question, not example question, so that will break. And so that's the prompt, and then I run the generate function like we did. We just pass the prompt, and I also just make it a little bit nicer. I make it sort of truncate itself and not display the question. Okay, but that's our baseline. And then the way we do the RAG, while that's thinking, is we basically just pass the context. So pass those, we pass all that context with the question. So we say, oh yeah, ask this question, but also take all this into consideration, like use your own model weights to determine what the answer is, but think about these things in your context. So we just pass that in the prompt. That's all you do with RAG. All right, so the raw response is actually complete garbage. It just keeps saying answer, 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 answer. So now the only difference between this and the baseline is that it has this context here, RAG context, which we created. Okay. Good. Let's go. Oh, example question is not defined. I called it question. Hopefully that works. Can you build a dual-sided RAG that feed one dataset like MedTech one, have it synthesized, pop it, and then run the same functionality on a separate dataset map? Yeah, absolutely. Okay, so now we can talk about, you know, how you'd sort of deploy these two together in the real world. So especially if you're using really small models, like you want them to do really specific things. So you might train it to just answer yes or no on like, is this paper relevant to, you know, my research on rocks or something? So yeah, like, and I'm a very specific type of rock, like read this entire paper. Is it related to this? And you just want your model to say yes or no, yes or no, yes or no. So you could probably train the 270M model to do that fairly easily. You show it a few papers about rocks and say, like, you know, find things similar to this. And then you have a model like that. And then you have, you could then pipe all those papers that you've checked, all the ones that say yes, you can put them into a RAG, and you would have a in the RAG you would have all those papers, and then you'd ask questions about it. Oh yeah, like write a literature review using this context, and you might use a bigger model for that, but it would have to use that context. And then within that, you might also have like some other question that says, before you look at all those, I need you to like reformulate the entire paper into a few like dot points or something. So you could have like multiple steps in your pipeline. Okay, so the retrieve response is actually garbage. As I said, maybe I used too many. I think. If you do top N, let's do 1. Maybe it'll work better then. Let's try again. Okay, so this time, we'll try that one more time. Oh yeah, so that time we got a good one. Anemia is a condition in which the body has fewer red blood cells than normal. Great, I think that's fairly accurate. It's much better than this one. One thing I glossed over or didn't really mention, models also, they may have been trained on specific structure as well. So this, I've put this like instruction colon, and then given an instruction question colon. But I just made that up. But some model providers, so Gemma, for instance, they actually use this syntax, and I had it in the notes. And we can see if we can get a better response. it was in the fine tuning part. So yeah, how did so they had this start of turn user. So you should ideally, or they say it performs best when you have this start of turn user, and then you have the user, and then you have an end of turn flag. So you then have this end of turn. Remember, this is just text. There's nothing like secret about it or anything. It looks like it's some important way that it has to be structured, but it's just text. So the way to do it might look actually something like this. So yeah, this might give us more informative answers by doing it this way, according to the authors of Gemma. It actually gave exactly the same response, but the default, let's try the baseline again without the baseline was up here. It probably will give a better result if I put in start of turn user, end of turn, start of turn model. Okay, let's try that. Let's see. So that's without the RAG. Okay, well, it gave there's probably a better baseline. The answer to the question, what is anemia, is anemia. So it's not a very good answer, but it's a response. But you can see how powerful RAG is there, so which is cool. Okay, so I think so that's RAG in a nutshell. I mentioned, yeah, I quickly mentioned that there's finding the documents that are similar and just injecting them into the prompt. That's like, I guess, a very naive way to do it. But modern RAG systems, yeah, that they can do this like query transformation where it's, instead of using like what is anemia, you can actually strip the what is and just look for anemia, and you can use the LLM to make that question sort of more better at searching in the vector space. And then there's this concept of re-ranking. So there's specific re-ranking models that will take the top 50 responses, and then it will look at them like for a second time and try and structure them in a better way rather than just finding anemia and the top keyword matches or something. And so there's like, yeah, more advanced things, and a lot of these come out in other workflows that you'll see. Okay, so fine tuning or RAG, that's about, I think, everything to sort of get you started. You can download models now. You can download whatever language model you want. You can pick a framework that you want. You can pick an embedding model that you want. You can get your data in the format that you need and transform it. And you've got a Keras workflow there to sort of get you started. So if you have any questions, click for the agent session.